and already whatever problem sheets I have given, you must practice them. So as I have said that we will have our first class test Sunday morning. Okay, all of you, Sunday morning 40 minutes class test. You want to begin it from 9 o'clock or 10 o'clock? Quickly reply. You don't have a choice. It is Sunday.
9.
9 o'clock. ठीक है. Sunday morning we will have our first class test. Starting from 9, just 40 minutes, not much, not much. Those who are attending my subject for the first time, let me tell you, whether it is online or it is offline, all exams are open book exam. So open book means open class note, and in online everything is open, no doubt. But even if in this subject midterm or end term exam happens to be offline exam, there also it will be open lecture note exam. So last 25 years, last 20 years, all the exams I am taking, that is open lecture notebook exam. And now it has become so popular that other teachers have also started it. Fine. But I started taking open notebook exam from 1993. So it was the first time, maybe not first time, but definitely one of the beginners in this country. Okay, so this class test or exam, you can refer anything you want, except you cannot talk to each other. That is the restriction. Fine. But you can, and that is why your class note has to be well prepared. If your class note cannot be on the computer, it has to be in handwritten form so that you can understand quickly. So you have to prepare your class note so that with the help of the class note, you can answer exam questions quickly. Okay, so class test or midterm exam or end term exam, you can always refer to your class notes. No problem. Okay? You can refer to your solutions also. Only thing, you cannot interact with each other during the exam. Not through mobile, not through email, not through WhatsApp, not through anything. Now please remember one thing. WhatsApp कौन सी कंपनी का है? You have any idea?
Metaverse.
WhatsApp is from Metaverse, and Metaverse belongs to whom?
Mark Zuckerberg.
Metaverse तो Facebook ही है ना?
Yes, sir.
So all these top people, Google, so I am in connection with them. So if you do anything wrong, you will get caught. Okay? So now you can take out, एक मिनट, कितने लोग आए हैं? 15. Okay. So let us go to our discussion today. पहले पढ़ो, फिर बाद में मैं एक्सप्लेन करूंगा. First you read it. You don't need to write it. Don't need to write it, anything. Just read it and then I'll explain. Now, today we will discuss how to handle situations when damping is not viscous. So, there are many examples where damping is not viscous. One of the example already we have seen, Coulomb damping. Fine. And today we will take up other kind of damping also where damping is not viscous. So what do we do? Because in last 2 weeks you have seen all our mathematical derivations, they are based on viscous damping. So question is, if damping is not viscous, what do we do? One of the concept that we apply is, even if damping is not viscous, harmonic force, it gives us a harmonic response. Okay. So even if damping is not viscous, we presume a harmonic force will give us a harmonic response. This is not 100% correct, but almost correct. I mean, okay, so our first assumption is, even if when damping is viscous, F0 sine omega t gives us a response which is harmonic. Now we will assume that even if damping is not viscous, a harmonic force will give us a harmonic vibration. However, how much will be amplitude? We have to find out what is the formula, how to calculate amplitude of vibration when damping is not viscous. But the common platform that we retain is that even when damping is viscous, vibration is also harmonic under harmonic excitation. Our assumption is, even if damping is not viscous, F0 sine omega t will give us harmonic vibration. Only thing, how to calculate x bar, that may be different. So this is first assumption. And with this assumption, we can proceed to handle if damping is not viscous. To do that, first what we do is, we find out how much work is being done by the damping force in one cycle. We find out how much work is done by the damping force in one cycle. So we begin with viscous damping and we calculate how much work is done by the damping force in one cycle. So this is the derivation. Now you write down everything as given in the PPT. I have explained and you write down neatly. I am giving you time. We are not in a hurry. You neatly write down whatever you see in the PPT, and if you have any, first to write down, and any mistake in my derivation, let me know. Anything you are unable to understand, let me know. This PPT I will discuss for 15 minutes because this is a beginning of a concept. try to understand the concept. Not only try to understand the derivation, try to understand the concept. But first you look at the derivation. You must note that limit of integration has changed here because the integrand has changed from dt to d theta. So theta is equal to omega into dt. So d theta by omega is equal to dt. Limit of integration, we have changed 0 to 2 pi because we are going to integrate a trigonometric function. And that is why limit of integration has been changed. And finally we get this pi c omega capital X bar whole square. Have you written it, all of you? बाकी है किसी का? Anyone who has a doubt in the derivation? Vinith?
So no doubts.
No doubt. Fine.
And
Now,
sir,
हाँ बोलो.
नहीं sir, नहीं, it's all right.
No, fine. Now, try to understand the concept. What is this energy? It is lost from the system. It is lost from the system. System loses this much of energy. And this much of energy comes from where? It comes from excitation force. So job of the excitation force is to supply this much of energy. Otherwise, system cannot lose this much of energy. So in every cycle, system loses this much of energy if amplitude of vibration happens to be x bar. Then system loses this much of energy. Now, here we go for our second assumption for non-viscous damping. For non-viscous damping, our first assumption was similar to viscous damping, a harmonic force will also give a harmonic response. This is almost correct, slightly wrong. I will not discuss that because that is at the research level. But this is not a highly inaccurate assumption. Fine. So first assumption is a harmonic force will give us a harmonic response even if damping is not viscous. First assumption. Second assumption is that even if damping is non-viscous, energy lost in one cycle, if it is equated with this value, then the corresponding C we can say as equivalent viscous damping. Try to understand what I am saying. Our damping is not viscous. we are replacing non-viscous damping by an imaginary model where damping is viscous and its coefficient of damping is C equivalent. So if these two situations are to be compared, then energy lost in both the case must be same. So we say that corresponding to the non-viscous damping, there exists an equivalent viscous damping such that energy lost in one cycle will be same in both the case. In both the case. How do we apply this concept? Let me explain with respect to Coulomb damping. So you just read it. You just read it. Don't write it now. First you read it and then you write it. For non-viscous damping, what is our concept? Non-viscous damping is replaced by an equivalent viscous damping such that energy lost per cycle will remain same. This concept we apply for Coulomb damping. So in a Coulomb damping, damping force is mu into N. So energy lost in one cycle will be, force is constant. So force multiplied by the displacement. Total displacement is 4x bar. In one cycle, total traveling of the mass will be 4 into x bar. Why? Because negative x bar to positive x bar, and then that is half cycle, and next half cycle positive x bar to negative x bar. So total travel is 4x bar. Force is constant for Coulomb damping. So force multiplied by total travel will give me total energy lost in one cycle. So for Coulomb damping, this is total energy lost in one cycle. Now this energy lost in one cycle, I equate with viscous damping energy lost. And then whatever C equivalent I get, this is equivalent viscous damping. So a Coulomb damping can be replaced by viscous damping where this is the coefficient of damping. And this comes out to be 4 mu n by pi omega x bar. This comes out to be 4 mu n by pi omega x bar. So this is basically a beautiful concept which is not 100% correct, but it works. It works. So try to understand the concept, and now you write down, and I will wait for another 5 minutes to digest how we handle a situation when damping is not viscous. What do we do? Even if damping is not viscous, we replace the mathematical model by an equivalent viscous damping model, where coefficient of equivalent viscous damping is calculated from the formula. This formula will vary from one non-viscous damping to another non-viscous damping. It will vary. So for Coulomb damping, this is the formula. For some other damping, formula will be different, because for some other damping, energy lost in one cycle will not be equal to this. So for different situation, first we have to calculate energy lost. We have to equate with the viscous damping energy lost, and that will give us the coefficient of damping. इसको लिखो. Anything you have not understood, you ask me.
Sir, how do we get 4 into x bar in the lost, like work done by the one cycle?
During Coulomb damping, the vibration is taking place. See, what is the displacement of the mass? Even in viscous damping also. Even in viscous damping, what is the displacement of the mass? It is 4x bar even in viscous damping.
Yes, sir.
But in viscous damping, I cannot say force into displacement because force is not constant for viscous damping.
Agreed, sir.
Because force is constant. Force is constant throughout vibration.
Yes, sir.
Viscous damping force is varying, so I had to go for integration.
Yes, sir. Yes, sir.
I'm waiting for somebody raising a big question. There is a big question in the result.
So we are never sure that we will know the amplitude of the vibration in the friction damping phase.
So how do you solve it then?
So that's exactly my question.
So you must realize this is a very peculiar situation. To find out coefficient damping, we must know x bar. However, x bar is calculated from the knowledge of C equivalent. If we don't know how much is C equivalent, we cannot calculate x bar. In case of viscous damping, x bar is calculated from the knowledge of C. What is the formula? X bar is F0 divided by square root of K minus M omega square whole square plus C omega whole square. Which means to find out x bar, we must know what is the value of C. And here we are saying that to know the value of C, you have to have the value of x bar. So this is a peculiar situation, chicken before the egg or egg before the chicken. So how do we solve it? Or do you think it is useless? Whatever we are talking about a concept that is useless. It makes no sense. I have given you a situation of Coulomb damping and I'm asking you to find out vibration amplitude x bar. Now to find out vibration amplitude of x bar, you need C equivalent value. And to find out C equivalent value, you need the amplitude value. So how do you start and how do you solve this peculiar problem?
We can put the C equivalent into the bar equation we have.
Correct.
Damping.
Correct. So
where we can form the equation.
Correct. So in the formula of x bar, we need the value of C. That C, we put the expression. Then we get an equation for x bar. So in the formula for x bar, wherever C appears, we put the formula for in terms of x bar. So left hand side also we have x bar, right hand side also we have x bar. We get an equation in x bar, we solve the equation, and finally we get this answer. This is the beauty, that we can solve the situation. It's not that peculiar. And finally, anyone who will solve the equation and who will tell me कि ये formula correct है, I'm giving you time, do it. You right hand side and left hand side, you combine, you will get an equation in x bar. If you solve it, you will get this answer. Is it correct or not? It will take time, but derive it.
Yes, sir, it is correct.
Now, if you look at the formula, so for Coulomb damping, what we can directly calculate amplitude of vibration. Fine. And we can draw the graph also. We can draw the graph also. This formula, it is not same as viscous damping formula. Viscous damping formula, this is viscous damping formula. Agree? This formula for vibration amplitude due to Coulomb friction is different from viscous damping formula. But where is the most interesting difference? This is the most interesting difference. If damping is viscous damping, pure resonance will not take place. Pure resonance means amplitude becoming infinity. In this case, amplitude will never become infinitely large. It will be maximum, but it will not be infinity. But in case of Coulomb damping, we cannot avoid infinite amplitude. Pure resonance will take place, and it will take place exactly at omega is equal to omega n. Here, the large amplitude takes place before omega is equal to omega n. It will not happen exactly at omega is equal to omega n. It will happen slightly before omega is equal to omega n. But in Coulomb damping, pure resonance will take place and it will happen exactly at omega is equal to omega n. So actual viscous damping is better than Coulomb damping, because in actual viscous damping, even near the resonant frequency, amplitude is finite, it is not infinite. But for Coulomb damping, near the resonance frequency or at resonance frequency, amplitude will be infinity. So Coulomb damping is more dangerous than viscous damping. Okay. Now, having understood this, so basically we have discussed how we can handle non-viscous damping. So what is the concept? Non-viscous damping is converted into an equivalent viscous damping model, and we calculate C equivalent by equating energy lost in one cycle. This is the concept. So we can apply this concept for quadratic damping. Fine. So these are some other examples of non-viscous damping. So if for quadratic damping, damping force is given by C x dot into x dot, modulus of x dot. Okay, so I am giving this mathematical expression, and this is solved in these two textbook. So this case has been, you have to find out equivalent damping, equivalent viscous damping. This is non-viscous, this is non-viscous, and this is the mathematical description how the damping force varies. In that case, we can calculate C equivalent by equating the energy. So this is a home task, and those who are more interested, they can go through the textbook of Thomson, textbook of Seymour Hinkle. There is another damping called structural damping or material damping, where when work done is proportional to amplitude square, alpha into amplitude square. So this is solved in Meyrovich textbook. I have one spare Meyrovich and one J.S. Rao Gupta book with me in my lab. Anybody who is in Nagpur, if they can come to the college, I can give the textbook for the semester, not for lifetime. Okay. I have one Meyrovich, I have one Rao Gupta textbook with me. Other textbook I have, but that is the only copy I cannot give you. But our library has 30-40 textbook of Thomson, but only one textbook of Seymour Hinkle. So from library, if they allow, you can issue it. So these other examples of non-viscous damping, I'm giving you as home task, but they are also available in textbook. I'm not going to solve each and every problem for you. I have given you the concept, and I have demonstrated the concept for Coulomb damping. So these are other cases where using the same concept, you can find out equivalent viscous damping. This is hysteresis loop. Here also C equivalent comes out to be alpha by pi omega. I will give you the PPT. Definitely. I'll give you the PPT, and this is home assignment. So I have explained only one example, that is Coulomb damping, but I have given 4 examples as home assignment. So this will be your homework, And whenever I say something as homework, quite likely a question will come in class test or exam. So you must pay attention to them. These are solved in textbook. Thompson, Meyrovich, Seymour Senkel. ठीक है? I will go to another chapter right now, but before that, on the concept of equivalent viscous damping, any question from anybody? Okay, then I'm going for our next chapter today. Our next chapter is today is periodic excitation. So till now the excitation force we have taken, it is harmonic. Harmonic means F0 sine omega t. I have already mentioned in the beginning that excitation force can be of three types: harmonic force, periodic force, and transient force. So right now we want to start our discussion on periodic excitation. Periodic excitation is not harmonic. Harmonic is periodic, but every periodic excitation is not harmonic. Don't confuse it. Harmonic excitation is definitely periodic, but all periodic excitations are not harmonic. For example, sawtooth, pulse excitation, sawtooth excitation, they are periodic, but they are not harmonic. So, a periodic excitation will repeat its value after certain time, that is known as time period. So, if the time period is tau, then the force will repeat its value after the time period tau. This is the beauty of a periodic excitation. It need not be a sine curve. It can be a sawtooth curve, it can be a pulse, rectangular pulse, but it will repeat it after time period tau. So we know from Fourier series formula that every periodic function can be written in the form of an infinite series, which is called Fourier series. Now, this Fourier series was given by Fourier long time back, more than 200 years. But this series is very important in engineering, very important in engineering, Fourier series. And then the next result which came from Fourier series is Fourier transform. So Fourier series and Fourier transform both are extremely important in engineering. Right now we are discussing Fourier series. Fourier series is series decomposition of a periodic function. This is called DC component or constant part of the function. And these are the varying component. One set, they follow cosine functions. Second set, they follow sine function. Omega is calculated from the time period by this formula, 2 pi by tau. Omega is calculated from the formula 2 pi by time period. So this Fourier series we know. I'm not going to explain Fourier series. What I'm saying is, suppose we have been given a periodic function as excitation. Can we calculate A0, A1, A2, B1, B2, etc.? If we can, then we can easily handle this situation also. So first let me discuss how we can calculate A0, A1, B1, A2, B2 like that. So this is the formula for calculating A0, A1, B1, etc. तो अभी आप लोग पहले फूरियर सीरीज लिखो अपना कॉपी में, एक प्रॉब्लम सॉल्व करने देंगे. सो राइट डाउन द फूरियर सीरीज फर्स्ट. how it, you already know, but you must have forgotten. So write down the Fourier series first. If you have written the Fourier series, then this is the formula how to calculate the coefficients. इसको भी लिखो, ढंग से लिखो, neatly, write it neatly. Write it neatly. So if the excitation is periodic, first that periodic function is written in the form of a Fourier series where coefficient A0, A1, B1, A2, B2, they are obtained by this mathematical formula. Once we obtain A0, A1, B1, we can easily find out the response. But first, our target is how to get these coefficients of the Fourier series A0, A1, B1, A2, B2, how to get them. So let us take up an example and see how the mathematics goes. So let me take this example. It is taken from, say, Morse-Hinkel. So this is a problem. We will solve this problem now. I'll give you the PPT, लेकिन problem समझने का कोशिश करो पहले picture से. And try to write down the equation of motion for the mass m. From the picture, try to write down equation of motion for the mass m. This is Camp-Follower mechanism, which you have studied in third semester, second year, third semester, Camp-Follower mechanism. As the cam rotates, the follower goes up and down. So this is the follower. Follower goes up and down. Depending on the cam profile, the follower movement will be decided. Here, what do we see? Cam profile is such that follower movement follows a sawtooth curve. Now, this is a periodic function. This is a periodic function. This is follower motion. Now, as the follower goes up and down, the mass will also go up and down because the mass is connected to the follower by a spring. And mass on the other side is also restrained by another spring and a damper. We want to know if follower movement looks like a periodic sawtooth curve, how the mass displacement will look like. Okay. So how this mass, which may be basically another process component, like in an IC engine, This may be the valve movement. Okay, this is the cam movement. In an IC engine, you know, valves are operated by rocker arm mechanism. Though they are driven by camshaft. So this is the cam, this is the follower, but actual motion is the valve motion, valve opening, which may not be same as the follower movement. No, we will show that this motion will be different from follower movement. Follower movement is this. Whereas the movement of the mass m, which is given by coordinate x, it will be different from x1. x1 is the follower movement, which is a sawtooth curve. Movement of the mass m, which is given by coordinate x, will be different. Our job is to find out this x. Karun, I leave it up to you. I have explained enough. I am not going to give you more hint. Go ahead, do as much as you can. अभी अपना दिमाग लगाओ. How we can find out x? what you have to do first, you have to first write down the equation of motion in terms of x and x1. And then in the equation of motion, you have to find out what is the excitation force. And you have to express the excitation force using Fourier series. First, you have to write down equation of motion, and then you have to find out what is the excitation force. Anybody who has done the equation of motion, who has written equation of motion?
Yes, sir.
Bolo.
Sir, of motion
Hmm?
m x double dot plus c
Huh?
m x double dot plus
Huh?
c x dot plus k x plus k1 into x minus x1 equal to 0.
So लेफ्ट हैंड साइड में x रखोगे तो राइट हैंड साइड में क्या आएगा?
k1 x1.
So you have to now write it as, so this is k1 x1, correct. So this is the equation of motion. And this is the excitation force. This is the excitation force which is written in a periodic function. And now you have to calculate the coefficient A0, A1, B1. So I will stop here today, but tomorrow when we begin, you must have the calculation of A0, A1, B1. Okay? So this PPT I am not sending you today, but I will send the coefficient, non-viscous damping PPT today. This discussion will complete tomorrow. This is our equation of motion. If we rewrite it, then K1 X1 is the excitation force which can be expressed in the Fourier series form. You have to calculate how much is A0, how much is A1, how much is B1. You have to calculate. And in this case, because this is K plus K1, natural frequency will be square root of K plus K1 divided by M. Natural frequency will be square root of K plus K1 divided by M. And this is my excitation force. And as I have said, excitation force can be split into, written in a form of a Fourier series where I can calculate A0, A1, B1. तो यहाँ तक आप लोग लिखो और कल क्लास में A0, A1, B1 solve करके ले आओ. Okay, so up to this third line you write it down, and tomorrow I want from you what is the value of A0, what is the value of A1, what is the value of B1. उसके लिए okay, up to this page I will give you the PPT today. By 1:30 you will receive the PPT up to this page, so that you can calculate A0, A1, B1, etc. ठीक है? चलो आज हो गया. I have another class. You also have another class. We'll stop. I'll give you the PPT up to last page in this discussion also. चलो आज हो गया. You can. I have to end. You can also